Right now, about 130 miles away from an Air Force base, there's a student pilot pulling 8Gs. They're sweating right through their flight suit, just frantically trying to dodge a surface-to-air missile.
Yeah, and the physical strain on their body in that moment is incredibly real. I mean, the jet they're flying is real.
But the missile itself doesn't actually exist.
Right, exactly. It's completely virtual.
It's being beamed directly into the cockpit displays by, a software engineer who's probably just sitting at a desk somewhere with a cup of coffee.
Which is wild, right? And that represents a complete inversion of how aerospace training has operated for the last century.
We're definitely not just teaching someone how to operate a vehicle anymore.
No, not at all. We are teaching them how to interface with this living, breathing system of systems.
Well, welcome to the Deep Dive. Our mission today is to pull apart the engineering and really the whole philosophy behind a very specific machine.
Boeing's T-7A Red Hawk.
Exactly. We have a lot of source material today directly from Boeing's official specs, their timelines, and recent press releases. We are going to look at how this one piece of technology represents just a massive multi-generational leap in how the U.S. Air Force trains its fighter and bomber pilots.
And we really need to dig into those specifications, the digital architecture, to understand how this aircraft completely redefines that boundary between physical reality and digital simulation.
To really get the magnitude of what the T-7A does, though, I think we have to look at the massive problem it was built to solve first, right?
Oh, absolutely. I mean, the reality for you listening to this in the modern world is that defense landscapes are just not static. They change constantly.
Right. Adversarial technology evolves at a blistering pace now.
It really does. So keeping a pilot mission ready means training them for scenarios that are highly complex and, frankly, genuinely deadly. And historically, you only had a couple of ways to actually do that.
Which usually involves some major compromises, if I remember the sources correctly.
Yeah. Big compromises. You could put student pilots in older, much cheaper jets, but those don't actually fly anything like modern fighters.
Right, they don't have the same feel or capabilities.
Exactly. Or, on the flip side, you could put them in actual fifth-generation fighters, like an F-35, but then you're burning through incredibly expensive airframes.
And taking on high-risk flight hours just to simulate a threat.
Right, which is just not sustainable from a cost or a safety perspective.
So if the end game here is essentially building a giant flying virtual reality headset, it makes me wonder, why do they even need a high-performance jet for this?
What do you mean?
Well, couldn't you just put these advanced digital displays in a slow, cheap propeller plane? Or maybe even a commercial jet and just beam the fake missiles into that?
I see what you're saying, but no, you really can't, because you just cannot fake the physics of combat.
Oh, good. The physical toll on the body.
Yes. A student pilot has to learn how their brain and their entire body reacts when the airframe is pushed to its absolute limits.
Right. If they dodge a virtual missile in a slow propeller plane, they aren't learning anything about the actual physical punishment.
Exactly. They don't learn how to manage those violent, evasive maneuvers. The T-7A is designed specifically to bridge that gap between basic flight training and those incredibly complex fifth-generation fighters.
And to do that, the physical machine basically has to be a monster, right?
Oh, it's a serious piece of hardware.
Yeah, let's get into the mechanics of that physical machine, because looking at the raw specs, they are staggering.
They really are.
I mean, this jet is powered by an F404 afterburning engine, and that power plant allows this trainer to reach a maximum speed of Mach 0.975.
Right, so it is brushing right up against the sound barrier.
Operating at altitudes up to 45,000 feet, and like we mentioned earlier, it is capable of pulling 8Gs.
And I think we need to pause on that because the physical toll of 8Gs cannot be overstated.
It sounds painful.
It is incredibly demanding. When a pilot pulls that kind of maneuver, gravity is literally multiplied by 8.
So if a pilot's head and helmet weigh, maybe 15 pounds normally?
Yeah, around there. Suddenly, they have to support 120 pounds on their neck alone.
Oh, wow. That's insane.
And it's not just the weight. Blood is violently being forced out of their brain and down into their legs.
Which is how pilots black out, right?
Exactly. G-force-induced loss of consciousness. So they have to physically strain. They use these very specific breathing techniques and muscle contractions, literally just to stay conscious.
And you just can't train that muscle memory in a simulator on the ground.
No, you have to train it in a real aircraft under real physical stress.
But it isn't just about speed and gravity here, right? It's also about the agility of the aircraft.
Oh, absolutely. The agility is key.
The specs say the T-7A can hit a 30-degree maximum angle of attack. Now, for you listening, angle of attack is essentially the difference between where the plane is actually moving and where the nose is pointing.
Right, which is a great way to visualize it.
So a 30-degree angle of attack means the pilot can tilt the nose of the plane aggressively upward, up to 30 degrees, while the momentum of the aircraft is still carrying it forward.
And they can do all this without the plane falling out of the sky or losing control.
That specific capability seems crucial for modern combat.
It is entirely crucial because fifth-generation fighters are incredibly agile. They sometimes border on being aerodynamically unstable just to allow for those rapid directional changes in a dogfight.
So by engineering the T-7A to hit that 30-degree angle of attack, Boeing is making sure the student pilot learns how to handle a plane that feels, I don't know, twitchy.
Twitchy, hyper-responsive, aggressive, all of those. They need to know what that feels like before they get into an F-35.
And if you look at the design, notice how compact the airframe is to achieve that agility.
Right.
It's only 47.7 feet in overall length.
Yeah, with a wingspan of just 30.6 feet, it's very tight.
And they somehow packed 4,500 pounds of fuselage fuel into it.
Right, which is a massive amount of fuel for such a small airframe.
Yeah, so by cramming that much fuel in such a tight, lightweight fuselage right next to that massive afterburning engine, they've created this thrust-to-weight ratio that perfectly mimics that aggressive agility.
Exactly. It isn't just small to save on manufacturing costs. I mean, it does save money, but it's small to intentionally force the student to handle a highly volatile machine.
But beyond just the raw engineering, there is also this very deliberate physical legacy built into this machine, isn't there?
Oh, you mean the red tail? Yeah, that is a beautiful detail.
Right. In March 2025, there was this breathtaking visual over the Mojave Desert. They flew a brand new cutting-edge T-7A Red Hawk in a tight formation alongside a World War II-era P-51 Mustang.
And both of them featured those bright, distinctive red tails.
Which isn't just some bold aesthetic design choice. It is a direct, permanent commemoration of the legendary Tuskegee Airmen.
Yeah, it really serves as a powerful visual bridge. You have this 21st century digital marvel lying right next to a mid-20th century propeller fighter.
It's an amazing image. The contrast is wild.
It is. Because while the aerospace engineering has changed beyond recognition, the human element, the courage, the legacy, the breaking of barriers, that remains the fundamental core of the Air Force.
So the red paint is a daily reminder to every student pilot climbing into that cockpit of the exact legacy they are inheriting.
Exactly. It grounds them in the history before they take off into the future.
Which is incredibly poetic.
Yeah.
But that actually brings up a massive friction point for me.
Oh, what's that?
Well, we are talking about upgrading the ultimate driver's ed car. It's like going from a basic sedan directly to an aerodynamically aggressive supercar that pushes Mach 1 and pulls 8 Gs.
Right, it's a huge jump.
Putting someone who is still learning the fundamentals of aerial combat into a machine this powerful seems incredibly dangerous.
Yeah.
I mean, how does a student pilot not just get completely overwhelmed by the cognitive load, not to mention the physical strain their very first time in the cockpit?
That is the big question. And the way Boeing mitigates that overwhelming cognitive load is by completely rethinking how a plane is built from the ground up. Well, the T-7A was digitally designed, built, and tested along a digital thread long before any physical metal was ever cut. They utilized extensive model-based verification.
Meaning they basically build a complete digital twin of the aircraft first.
Precisely. They used massive amounts of data to simulate the aerodynamics, all the internal systems, and even the potential failures.
So they were working out the bugs in a supercomputer rather than, discovering them midair during a test flight.
Right, which saves time, money, and obviously lives. But for the student pilot actually sitting in the cockpit, the real mechanism that prevents overwhelm while still preparing them for a real war is the ILVC training system.
Okay, ILVC. That stands for Integrated Live, Virtual, and Constructive Training, right?
That's the one.
Let's break down how that actually works in practice, because the technology driving it is genuinely mind-bending. The sources mentioned the cockpit features an 8K projection system for high-fidelity mission rehearsal.
Right, so the live part of ILVC is the physical aircraft itself. Like we discussed, the pilot is up there feeling the 8Gs, they're managing the real throttle and fighting the actual physical forces of the air.
But then you have the virtual and constructive parts.
Exactly. That means the aircraft's computers are actively receiving synthetic data and displaying it on the pilot's 8K screens and right onto their helmet visors.
As if it were happening in the physical space right outside the canopy.
Yep. It seamlessly blends the real world with the digital simulation.
There is this incredible scenario in the press releases detailing a ground-based training system software engineer. His name was Steve Dobronsky.
Oh yeah, I remember reading about that test.
Yeah, he was sitting at a console on the ground, just visually tracking a computer-generated jet on his office screens. He was actively flying an engagement within a simulation.
But the telemetry driving the virtual jet he was fighting against...
Right, the telemetry was being beamed in real time from an actual physical T-7A aircraft that was flying 130 miles away.
That is what they call untethered operations in action. The physical jet and the digital network are just perfectly, seamlessly synchronized.
It's unbelievable. So a pilot in the physical T-7A can be flying through completely empty, completely safe airspace over a desert somewhere.
Yeah, just blue skies outside the window.
But on their advanced visual displays, their radar is lighting up. They are navigating through a highly contested combat zone populated with enemy fighters and ground-to-air missiles.
Exactly. And pre-programmed scenarios can be selected right from the cockpit by the instructor sitting behind them, or they can be coordinated dynamically from the ground by someone like Dobronsky.
So they are literally doing man versus simulated enemy engagements midair.
They are. It's a completely new paradigm for training.
Well, hold on, though. If they are projecting fake enemies onto the visor and managing this entire war from a desk on the ground, aren't we essentially just building a multi-million-dollar flying video game console?
I hear that critique a lot, yeah.
Because, I mean, how do you prevent a 22-year-old student pilot from treating this exactly like a video game where they have extra lives? If the enemy isn't actually there to shoot them down, don't they lose their respect for the deadly reality of combat flight?
That is a very valid pushback, and it's actually the primary concern with any synthetic training. But the mechanics of the T-7A are specifically designed to prevent that gamification.
How do they prevent it?
Because the pilot simply cannot treat it like a video game. The physical consequences of their decisions in the air are immediate and violent.
Ah, right. The G-forces.
Exactly. If they yank the stick to dodge a virtual missile, the physical jet violently responds to that input, and they still feel those 8 Gs crushing them into the ejection seat.
They still have to manage their actual fuel consumption, monitor the real engine heat, and, keep the plane from actually stalling.
Right. The synthetic threat forces a real-world physical reaction. You sweat just as much dodging a fake missile as a real one if you're pulling 8 Gs to do it.
And the way the jet translates those physical reactions is through fly-by-wire digital controls, correct?
Yes, fly-by-wire is central to making this work.
To give a quick explanation of fly-by-wire for you listening in older planes, when the pilot pulled the stick, it physically pulled a steel cable that mechanically moved a flap on the wing.
Very mechanical, very direct.
But in a fly-by-wire system, there are no direct physical cables. When the pilot moves the stick, they're essentially just asking a computer to perform a maneuver.
Right, and then the computer calculates exactly how to move the various flaps and rudders to make that specific maneuver happen safely.
So because the flight controls are managed by software rather than physical cables, the T-7A can digitally mimic the handling characteristics of entirely different aircraft.
Which is brilliant. The computer can be programmed to make the controls feel heavy and sluggish if they want to simulate a bomber, or it can be programmed to make the jet feel hyper-nimble.
Directly replicating the specific handling qualities of those advanced fifth-generation fighters we talked about.
Exactly. So they are receiving the physical punishment and the aerodynamic reality of flying a fifth-gen fighter. But the combat scenario itself is completely synthetic.
That dramatically reduces the pilot's exposure to high-risk flight hours. I mean, to practice dodging a surface-to-air missile in the past, the Air Force had to set up incredibly complex, expensive physical exercises with real aggressor squadrons.
Yeah, costing millions of dollars just for one afternoon of training.
Now, they practice those deadly scenarios virtually multiple times while safely in the air.
Right, building that crew station situational awareness and decision-making confidence without any of the operational risk.
Which naturally brings us to the logistics of sustaining an aircraft like this. Because usually when you introduce a bleeding-edge system, I mean, a flying network node beaming data 130 miles away, it translates to an absolute maintenance nightmare.
Oh yeah, advanced technology almost always requires highly specialized, incredibly expensive upkeep.
So how does the Air Force actually afford to keep a fleet of these running?
The answer lies in how the aircraft is architected. The T-7A was designed with a huge emphasis on pragmatism and lowering the total life cycle costs.
And the core of this pragmatism is what they call the open mission systems architecture, right?
Yes. Open mission systems, or open architecture, is essentially about decoupling the hardware from the software.
Meaning they aren't permanently locked together.
Right. In legacy military jets, the sensors, the radar, the display screens, they were all hardwired together with very specific proprietary code.
So if the military developed a new radar system 5 years later,
Installing it meant literally tearing the physical plane apart and rewriting all the foundational software just so the new systems could talk to the old ones. It took years.
it's kind of like the evolution of the smartphone, if you think about it.
Oh, that's a good analogy, yeah.
Because in the early days of cell phones, the hardware and the functions were locked together. If you wanted a phone with a better calendar or a new Snake game, you had to go buy a completely new physical phone.
Right, you couldn't just update it.
But now, smartphones have a universal digital spine and operating system. You keep the physical hardware, but you swap out the apps and update the software instantly over the air.
And the T-7A operates on that exact same principle. It has a universal digital spine.
So when real-world threats evolve or a new sensor is invented, the Air Force can just plug the new technology in.
Exactly, they plug it in, and the open architecture recognizes it instantly. It's basically plug-and-play warfare.
That plug-and-play approach has to solve one of the military's biggest financial headaches.
It absolutely does. It allows for the rapid integration of evolving technologies without grounding the fleet for months of retrofitting.
And I imagine it helps with training syllabuses too.
Definitely. If they need to shift the multi-role mission training from, say, a fighter pilot syllabus to a bomber pilot syllabus, the system scales and adapts to meet those diverse requirements entirely through software updates.
But the pragmatism of the design isn't just software. It extends deeply into the physical maintenance on the ground as well. Like if you look at the physical design of the cockpit, they intentionally went with side-opening canopies.
Right, and that side-opening canopy is a direct concession to the mechanics working on the flight line.
How so?
Well, instead of having a traditional clamshell canopy that opens upward and just gets in everyone's way, a side-opening cockpit allows maintainers to easily lean right into the crew station.
So they can access the ejection seats and the internal avionics without needing specialized cranes or awkward scaffolding.
Exactly. It just makes everything faster and safer for the crew on the ground.
Speaking of the ejection seats, the sources note that the egress system in the T-7A is undergoing intense scrutiny to ensure it is the safest of any trainer in the entire fleet.
Yes, joint Boeing and U.S. Air Force teams are conducting ongoing, really rigorous data analysis of the ejection seat performance and the entire escape path.
It really highlights that safety isn't just, a box they check during the initial design phase. It is an ongoing model-based verification process where they are constantly running the numbers to protect future aircrew.
And beyond the egress system, they also structured the avionics compartments and the maintenance panels to be easily accessible from the ground.
Which dramatically reduces the downtime for both planned inspections and those unscheduled maintenance issues that always pop up.
But honestly, the most brilliant logistical move Boeing made was the integration of common subsystems.
Right, the jet uses shared, trusted components from existing 4th and 5th generation aircraft.
So building on your smartphone analogy from earlier, not only are they decoupling the software, but when a physical piece of hardware actually does break, the supply chain is already fully established.
The mechanic on the flight line doesn't need to go learn an entirely new mechanical language.
Nope. And the Air Force doesn't need to spin up a brand new manufacturing pipeline for every single bolt and sensor. They are utilizing parts and infrastructure that the military already stocks, knows, and trusts.
By streamlining the logistics and utilizing common parts like that, you keep fleet availability incredibly high and the total ownership cost really low.
Which is the ultimate goal, right? Boosting pilot throughput. The Air Force desperately needs to train more pilots faster, but they cannot afford to bankrupt the sustainment budget to do it.
The T-7A seems to solve the throughput problem and the budget problem simultaneously.
It does, and all of this theoretical efficiency and digital architecture is actually officially translating into reality right now.
Yeah, if we look at the program milestones in the sources, there is a crucial date that just hit. In May 2026, the T-7A Red Hawk was officially cleared for low-rate initial production.
And May 2026 is really the turning point. It means the aircraft is no longer just a prototype being tested in a vacuum.
Right. This digitally thread-woven system of systems is actively rolling out of the factory and onto the runway.
It is officially transitioning from the testing phase into the hands of the operators.
If we pull back from the aerospace engineering for just a moment and look at the broader philosophy of this machine, There is a really profound takeaway here for anyone trying to build something new today.
Oh, absolutely. You don't have to be a military pilot or an aerospace engineer to apply the lessons of the T-7A to your own industry.
The concept of digital twinning, of building a completely adaptable, model-based digital verification system before you ever commit physical resources, it's just the ultimate blueprint for modern problem solving.
They didn't just build an airplane. They built a platform that fully expects the future to change.
Right, by establishing open architecture and prioritizing maintainability from day one, they ensure the machine will never become obsolete.
Exactly. Whatever field you operate in, designing your processes to be easily updated and testing your ideas in a rigorous, data-driven virtual space is exactly how you survive in a rapidly changing environment.
That brings me to a final concept I want to leave you with today. We started this deep dive by exploring how the T-7A utilizes ILVC training to project 8K synthetic threats directly into the pilot's helmet display.
Right, blending the real and the virtual.
We established that the pilot feels the bone-crushing physical G-forces of dodging a missile that ultimately only exists as lines of code in the software. The physical and the digital worlds are flawlessly, seamlessly overlaid.
The human brain in that cockpit is processing synthetic data and physical pain simultaneously. It's a completely new human experience.
So here is something to mull over. Human intuition is fundamentally built on physical experience, right? It is built on recognizing patterns in the tangible physical world.
Right.
But if a pilot's training relies heavily on a system where they literally cannot distinguish a virtual threat beamed into their visor from a physical threat out the window, what happens to that human intuition?
That's a huge question.
If the human brain learns to react to synthetic data exactly as it reacts to physical reality, experiencing the exact same adrenaline spikes, the same physiological stress, the same physical toll, does the boundary between the physical and digital world effectively cease to exist for the next generation of operators?
It really makes you wonder.
When you strap into a digitally native system of systems like this, maybe you aren't just learning how to pilot an aircraft anymore. Maybe you are learning how to live entirely within the network.